Welcome to the third round of our webinar series 2D-MAT, 2D Materials in Tribology. Today with Professor Alberto Rota with friction mechanisms of MoS2 at the multiscale, and Professor Carsten Gachot, who will speak about a new take on the design of in-situ formed high-performing low-friction tribofilms. Before we start, we want to thank our sponsors for their support. We are sponsored by the two MDPI journals Coatings and Lubricants, as well as Frontiers in Mechanical Engineering and Arctic Instruments. Hello everyone, welcome to 2D-MAT, 2D Materials in Tribology, our webinar series hosted by Professor Dr. Andreas Rosenkranz and myself, Philipp Grützmacher from Vienna University of Technology. Today we have two very exciting speakers again, which is Professor Alberto Rota from the University of Modena in Italy and Professor Gachot from also Vienna University of Technology. Maybe Andreas wants to introduce himself also for a short.
Yeah, hello everybody. As Philip already said, we very much welcome you to the third webinar. Today we have the first European couple after two speakers or series from the States. My name is Andreas Rosenkranz. I'm professor for material onto tribology, and I'm very much looking forward to the two presentations today.
Before we start, a friendly reminder for the participants, please keep your video and audio off so we don't disturb the speakers during their talks. And now, we would like to start with Professor Alberto Rota from University of Modena, who will talk about the friction mechanisms of MoS2 at the multiscale. Yes, we are looking forward to a interesting, inspiring talk, Alberto.
Yeah, I'm trying now to share the screen. Let me know if you are able to see.
Not yet.
Yeah, wait. Okay.
It's coming.
Yeah.
Yes.
Okay.
Yes, we see it.
Okay. Okay. So, of course, thanks very much to the organizer who invited me to give this speech and the opportunity to participate to a very interesting initiative related to the materials. Today I will talk about one of this 2D material, which is the molybdenum disulfide, as you can see from let me iconize, yeah, okay. If you can see from the title, so I will talk about the friction mechanism of MoS2. I would say at the multiscale, because we managed to measure the tribological properties at the macro scale, from the macro scale down to the nanoscale. Okay, as you can see, and thanks to the chairman, my name is Alberto Rota, and I am a member of the University of Modena and Reggio Emilia, which is located in the north of Italy. And I have also collaboration with the CNR, which is another organization in order to give research in Italy. Related to MoS2, just as a brief introduction, first of all, who is MoS2? Probably most of you know who is MoS2, but just to summarize that, I give you these slides. MoS2 is a 2D lubricant. It means that as most of this kind of material, it has a particular crystal structure, and which is characterized by parallel plane, where the atoms are strongly bonded in plane and weakly bonded out of plane. It means that each plane is able to slide with respect to the other very easily because of the very weak bonding between the planes. And in a way, it's this behavior is very similar, and the structure is very similar to graphite, because also in that case we have that the atoms are organized in the hexagonal structure, and in the same way they are very weakly bonded out of plane. For these reasons, the tribological performances of MoS2 are very good, and for this reason, this is also called a solid lubricant. And this is also the reason why it has been used since ages in order to lubricate sliding contacts, even if the real mechanism was not really understood yet. But we may say that the best, let's say that the most important application which started in the beginning of the last century is related to aerospace application. This is related to the fact that MoS2 works very well in absence of humidity. More or less the contrary with respect to graphite. And that's why, let's say, this particular characteristic of MoS2 attracted the attention of the NASA in the middle of the last century. Here you can see the main, let's say, important things related to MoS2. First of all, the modern use MoS2 can be considered to start with this patent here in 1927, and since that time there has been a very huge and important development in the study and in the usage of MoS2. And what I want to underline, particularly related to this material, is related to the failure of MoS2 and to the dependence of the sliding properties on the structure and on the composition. And related to this last aspect, so the composition, in the very, let's say, last 10 years, 20 years maybe, there has been a very important development also in doping this metal in order to further improve the tribological properties also in presence of humidity. So still related to the introduction, I have to say that in order to produce MoS2, of course, there are many methods, but probably the most used one is related to the deposition by means of physical vapor deposition technique. And in this case, the film that you can generate can be, let's say, sketch with this model, which has been proposed by Spolvins, where the first layer here is formed by more or less 100 nanometers of a dense and disordered zone. And the truth is that this first layer presents not really good tribological performances. But if you go further in the deposition, you have the generation of another layer composed by a dense and equiaxed zone. And in this case, we have, you can see very good tribological performances, so low friction and low wear. And if you continue in the deposition, you have the growth of this third layer, which is composed by a columnar structure where the basal plane of MoS2 are perpendicular to the surface. And still from the work of Spolvins, here you can see a view with the SEM of the surface of a PVD film, where you can see this particular needle-like structure, which represents the top of the columns in the sketch. Okay, going to the sliding models, the truth is that in this case, we have two most important hypotheses related to the sliding. One is proposed by Spolvins himself, and the other is proposed by Fleischhauer. Spolvins states that the lubrication is supported mainly by the Equiaxed Zone, so from this region, while the presence of the column does not really contribute to the sliding, and sometimes they can be also detrimental because they represent an abrasive third bodies. Opposite to this scenario, we have the opinion of Leschauer, who says that the presence of the column here are mandatory, let's say, in order to have good tribological performance, because he previewed that the sliding of the counterbody induces the bending of these columns in order to align the basal plate to the sliding direction. And if you look at these images from his work, you can clearly see what he wanted to communicate, that the sliding of the counterbody induced the bending of the columns in order to improve the tribological performances of the material. Okay, and finally, we have another important issue related to MoS2. So the failure of MoS2 in presence of humidity. In this case, again, we have two hypotheses. The whole one, let's say I call this the whole one and the novel one. The whole one preview that the presence of humidity induces the oxidation of the material, and in particular the generation of OMO3, which is an abrasive material, and the generation of these oxides induces the progressive failure of the coatings in presence of humidity. But other guys still at the middle of the 19th century proposed another solution related to these aspects, because they observed that the coefficient of friction is, let's say, slightly decreases, increasing the temperature of the substrate. And they explain this experimental evidence, supposing that the presence of water molecule can physisorb and diffuse in the bulk and sticking to the edge of the basal plane, and so impeding the lamellar easy shear. Actually, there is no consensus related to these two hypotheses. Somebody states that it's the oxidation that induces the failure of MoS2. Some other states that it's the physisorption of water molecule. So our intent is to understand more about the fundamental mechanisms related to the friction properties of MoS2, and in order to do that, we deposit very thin films of MoS2 on a single crystal. We choose to deposit 200 nanometers of MoS2 in order to avoid the growth of the columnar structure, in order to see if effectively it is the presence of the Equiaxed zone that support lubrication, or if it is the presence of the columnar structure. And we also want to clarify the role of water physisorption in order to see if, of course, it's physisorption or if it is oxidation that induces the failure of MoS2. We selected silicon as a substrate because in the form of single crystal, it presents a very flat surface, and so we can avoid the effect of surface morphology. And in addition, silicon is not a contaminant of MoS2, and so we can be sure that there are no effect of the substrate in the chemical characteristics of the coating. Okay, in order to generate this film, we use the physical vapor deposition magnetosputtering technique. Here you can see a sketch of the machine. In this case, the material is deposited in a in a vacuum chamber where you have the target, which is composed by MoS2, and the substrate in the top part of the chamber. So inducing a plasma and a sputtering of the plasma on the target, you have the generation of a flux of molybdenum and sulfur atoms towards the substrate, and the condensation to the substrate generates the final fins. Here you can see the appearance of the coating that we have made. The top view here, you can see that there are no evidence of the needle-like structures, and this is evident from the top, but also from the cross section. There are no evidence of the columns, and so more or less we are in the so-called Equiaxed zone. By means of Auger spectroscopy, we also characterize the stoichiometry of the film, and looking at the table, you can find that the film is stoichiometric. We have a small amount of oxygen, which is related to partial oxygen inside the chamber, but looking at the chemical, let's say at the spectra of the Auger, from the Auger spectroscopy, we may say that oxygen in this case is a residual oxygen inside the crystal. Okay, related to the tribological performances, we measured the coefficient of friction as a function of the sliding distance by means of a ball-on disc tribometer. Here you can see the main characteristics of the test. I just want to highlight the fact that the counterbody is made of steel, 100 chromium 6 steel, and the ball has 4 millimeter in diameter. The tests have been performed in 3 different conditions. So humid air, room temperature, the green line, dry air, room temperature, it means absence of humidity but presence of oxygen, which is this light blue. And in absence of humidity and absence of oxygen, so in nitrogen atmosphere at room temperature. And finally, in humid atmosphere, but a slightly higher temperature with respect to room temperature. The results shows that if you do the measurements in humid air, you have a coefficient of friction which is more or less around 0.18, and the failure is reached at about 10-12 kilocycles. When you move to the dry air, you have a very important decrease of the coefficient of friction, which is now around 0.5, 0.7, and the failure in this case has been reached at about 15 kilocycles. And if you do the measurement in nitrogen, you get the best performance, because in this case you have a coefficient of friction of about 0.02. And in this case, we were not able to reach the failure of the coatings, as you can see. These first results clearly show that even if we have not the presence of the columnar structure, we still have a very important performances of MoS2, which is able to support lubrication. So from this experiment, we can support the thesis of Spaulding's related to the sliding model. But from the last test that we did, so the measurement in presence of humidity, but at 75 Celsius degree, you can see that the coefficient of friction is clearly lower with respect to the measurement at room temperature. And the most important thing is that we did not reach the failure of the coating. And considering that 75 Celsius degree is enough to induce water physisorption, but not enough to induce the oxidation of the coating, this is the first evidence that probably at room temperatures, the failure is related to the physisorption of water molecule and not to the oxidation of the coating. In order to deepen these aspects, we repeated the similar experiments. And in this case, we checked the coefficient of friction and also the appearance of the ball counterbody at different temperatures. So we start at room temperature, we move to 40 degrees, 55 degrees, 75s, and then back to 55, 40, and room temperature. So we did a cycle in terms of the temperature of the coating. And what you can see is that the coefficient of friction started at 0.1, and then it drops at 0.01, 0.02 at the higher temperature here. And then we restore again the initial value of the coefficient of friction when we go back to room temperature. And more or less the same, let's say, the same results can be observed qualitatively if you look at the ball counterbody, because at room temperature you have a very large amount of debris on the counterbody here. The debris disappears as soon as we heat the surface, we heat the substrate here, so 40, 55, 75s. And when you go back to room temperature, again we found this very big amount of debris. This means that the process of heating the substrate induces a reversible process. So still we are supporting the thesis of water phase absorption and not of oxidation of the coating. But the final test, which represents more or less the smoking gun about this topic, is reported here, and it is what we call the pump and purge experiment. So we measure again the coefficient of friction as a function of the cycle of time, if you can see. But in this case, we change in real time the condition of the sliding, of the, let's say, of the ambient. So we started the measurement in presence of humidity here, and you can see that after some time you reach the steady state at 0.2, and as soon as you induces the flux of nitrogen here, you have the decrease of the coefficient of friction at more or less 0.1, 0.01, or 0.02, as already observed. If you recover the initial condition, we have again the restoring the coefficient of friction here, and then again nitrogen. But now in the following step, we introduce pure oxygen. So this step here and here, we have that the chamber is saturated by pure oxygen, which is the, let's say, most favorable condition of oxidation. But anyway, you observe a very low coefficient of friction. And if you look here at this stage, here we have fluxed here nitrogen and then immediately oxygen. And again, you can clearly compare the coefficient of friction, which stays again very low in the order of 0.02 or 0.015, something like that. So there is no difference on the coefficient of friction if we flux nitrogen or pure oxygen. And this means that the oxidation plays a very minor role in the case of the failure of the coating, at least at room temperature. Okay, we then wondered what is the role of the ordering of the structure. And in order to do that, we analyze the coating and the counterbonding by means of Raman spectroscopy. In this part of the study, we were inspired by this work here, which has been published. Oops, sorry, what happened? Yeah, which has been published by David and co-worker. They show that here, this is the Raman spectrum related to MoS2 deposited by means of a magnetosputtering technique. And here you can find the feature of MoS2, and in particular, you have to focus on this feature here at 377 in the Raman shift, and in this feature, which is this broad peak at 253. After the annealing of the coating, which in principle increases the order of the film, you have that the structure here at 377 gets sharper, so taller and sharper, and the features related to 253 decreases. So what we did, we took the Raman spectrum for the film as deposited, the black spectrum, and we compare it with the spectra collected on two different weather tracks. One is recorded considering a sliding velocity of 0.1 meter per second, and the other related to 0.4 meter per second. And it is clearly evident that the peak at 377 got taller and thinner with respect to the as deposited film. And in the case of 0.4 meter per second, we also observe a decrease in the features, in the broad features related to 223. This is the first evidence of recrystallization of the coating, which probably has a role in the performances of the material. And again, we also still using the Raman analysis, we want to deepen the aspects related to the measurement in air with respect to the measurement in vacuum. Here I reported the images that you have already seen related to the measurement in air at 1 Newton load, where you can see the presence of the debris. These debris are really not adhere to the substrate, because gently cleaning the surface, you can see the remotion, the complete remotion of this debris. Well, before cleaning the counterbody, we perform a Raman analysis on this region where the debris are present and in the wear scar. And what we obtain is reported in this graph here, where the green spectrum corresponds to the region with the presence of the debris, while the blue spectrum represents the analysis on the wear scar, so in the middle of the wear scar. And as you can see, the debris are composed by molybdenum disulfide, where there is no evidence of the oxidized layer, which has a feature around 800 centimeters to the -1, and it is possible to see the generation of the debris if we irradiate with an higher power of the Raman analysis, because in this case you can see the generation, the growing of this new structure, which is related to the oxidation of the coating. With Raman analysis, we also analyzed let's say the crystallographic order of the coating, increasing the load. So we repeated the experiments at 1 Newton, 2 Newton, 3 Newton, 5 Newton, and 7 Newton. And again, we look at the shape of the peak here at 375. And again, we found a recrystallization of the material related to the sharpening of this peak, but we did not find any dependence of the recrystallization to the load. Repeating the same analysis, the same analysis in vacuum, we have that even before cleaning the surface here, we do not have any evidence of debris on the surface, but we can observe the presence in the wear scar of this dark, let's say dark area. Well, doing the analysis, the Raman analysis on this part here in the black part, and using the higher power, the one that on the debris generates the oxidation, you can see that clearly see that here in red we have the presence of the MoS2 film. So we have the generation of a tribofilm composed by the molybdenum disulfide, which is probably the reason of the low coefficient of friction experienced in vacuum or in absence of humidity. And again, we analyze the let's say the order of the film, still analyzing this feature in the Raman spectra at different load. And again, we found that this peak gets narrower, and also in this case we did not find any dependence on the load, but the recrystallization seems to be more effective in the case of measurement in vacuum with respect to the case of the measurement in air condition. And this is probably contributes also to the best behavior that has been recorded in absence of humidity. Taking, let's say, considering the results that we found at the macro scale, we wanted to deepen the aspects of the intrinsic friction mechanism. And in order to do that, we have to move to the nanoscale. So we measure, again, the tribological properties, but applying lower load and with smaller contacts, our area of contact. So we use AFM. And in order to study the role of order and disorder of the coating, we select two different samples. One is the crystalline MoS2, so the mineral of molybdenite, and the other one is a let's say, quasi-amorphous MoS2, so our polycrystalline coating. In order to measure the tribological properties, we use AFM, but as we saw, the best performances has been found if the two surfaces that slides are made both of MoS2. And in order to have again this condition, we cover standard AFM tips with 100 nanometer MoS2 by means of PVD. And here you can see the AFM tip covered by MoS2, where you can clearly recognize the needle-like structure. So we use this kind of tip and we measure the coefficient of friction. In order to do that with AFM, what you have to do is to measure the lateral force as a function of the load. Of course, the slope of the resulting curve represents the coefficient of friction. So we did this experiment for amorphous coupling. So our tip against the polycrystalline film, and in the case of amorphous crystal coupling, so in the case of our tip against the molybdenite. And we did the experiments in absence of humidity, the red curve here, and in presence of humidity, so the blue curve. And the results after averaging all the data are reported in the table. So in the case of amorphous coupling, we have that coefficient of friction in dry condition is 0.41 and in humid condition is 0.58. This more or less is similar to the trend that we found at the macro scale, but is very different in terms of absolute value. And in particular, we have that the difference from dry to humid condition is very different. But this is probably related to the fact that from the nanoscale to the nanoscale, there are many differences which are related to the materials, which are related to the different load that we are applying, to the different area of contact and others. So these are probably the reasons which is related to the different behavior at the nano and at the macro scale. When we move to the amorphous crystal coupling, in this case, we have that coefficient of friction drops to 0.012 in the case of dry condition and 0.013 in the case of humid condition. So as expected, moving from amorphous to crystal structure, we have a very huge decrease of the coefficient of friction, because in this case we have the sliding of crystal against an amorphous condition with respect to the previous case. But the most important results is related to the fact that in the case of amorphous crystal coupling, there's no difference of the coefficient of friction from dry to humid condition. This can be explained to the fact that if it is true that it's the water physisorption on the boundaries of the grain boundaries that is the origin of the failure of MoS2, we have to expect that in the case of a crystallographic feature, the crystallographic structure, the density of the grain boundary is very limited with respect to the amorphous scale. So in the case of a crystal, the number of water molecules that can physisorb and penetrates into the bulk are are much less with respect to the amorphous case. In order to better understand the physical mechanism, we also perform a MD simulation thanks to the collaboration with the group of Professor Polzar at the University of Prague. I'm not really expert in molecular dynamics simulation, so I don't want to enter too much in details in these aspects. I just want to highlight the fact that MD simulation have been done using the contact of two amorphous slabs in the case of amorphous coupling, and amorphous slab versus crystalline sample in the case of amorphous crystal coupling. And the load, the pressure that has been applied was 5 gigapascal, and the velocity was 5 meters per second. The results are reported here in the case of amorphous on the top part and amorphous crystal in the bottom part. This image represents the beginning of the experiment, so 0 picosecond, after 500 picoseconds, and after 1000 picoseconds. In the case of amorphous coupling, you can see that the slidings of the top part with respect to the lower part only generates a deformation of the structure. And why in the case of amorphous crystal coupling, we have that the application of the shearing force induces the slippage of the plane with respect to the others. And this is clearly evident if we look, sorry, I'm not able, yeah. If we look at this video here, this is for amorphous coupling. You can see that the application of the force only generates the deformation of the structure. And of course, this means that the coefficient of friction is far higher with respect to the other case. If we move to the other video here, you can see that there is the stick slip of, in this case, of the second place with respect to the third. And again, we have another slip event of the first layer with respect to the second, and so on and so forth. So also in the case of the simulation, we can generate this friction force as a function, frictional force as a function of the load. And again, we can calculate the coefficient of friction in the case of the simulation for amorphous and amorphous crystal case. In this case, we are able only to do this in dry conditions, so in absence of humidity. And the comparison with respect to the experiments shows that in the case of amorphous coupling, we have a perfect agreement between simulation and experiments. And in the case of amorphous crystal pairing, we have that, again, the coefficient of friction is lower with respect to the case of amorphous, even if the difference with respect to the experiments is much higher as well. So in order to understand this, we have to do some consideration. Related to the difference of the coefficient of friction between dry and humid atmosphere, I have already told you that this is related to the very different experiments. And in the case of the difference of the coefficient of friction from, let's say, in dry nitrogen in the single crystal case, we have to consider that in a case of crystal coupling, we have that during sliding, let's say the sliding process is only related to the overcoming of the van der Waals forces. And this, let's say, explain why in this case the coefficient of friction is far lower with respect to the amorphous case, where in this case the slidings that does not only preview the overcoming of the van der Waals forces, but it is related also to other phenomena such as the breaking of covalent bond that can form during the surfaces because of the different crystallographic structure. And related to the difference here between, let's say, this value and this value and this value, this has been ascribed to the fact that during in the molecular dynamics simulation, the model assumes that we have the commiseration between the sliding plane. So this is the most dissipative scenario, which is not the case of the experiments. We cannot control exactly the orientation of the crystal of the crystal. Okay, I can let's say do some consideration, general consideration related to the to the work on this particular system, what I showed you is that 200 nanometers films are able to support lubrication despite the absence of the columnar structure. And this, in a way, support the model, the sliding model from Spalbins. Heating to a temperature slightly enough to induce the water desorption, you can have very good tribological performances even in presence of humidity. And this suggests that oxidation is not the main origin of MoS2 failure. This has been proved also measuring the coefficient of friction in a saturation of oxygen, which shows that even if oxygen is always present in the ambient, we do not get the worst tribological performances of MoS2. And we also found that in absence of humidity, we have the generation of a tribofilm, which is very strongly adhered to the surface. And this is probably the reason why, in absence of humidity, we have this very good tribological performance of MoS2. We also found that by means of Raman analysis, the sliding in both in the conditions, so in presence of humidity or in absence of humidity, we have that the sliding induces the recrystallization of the film that probably contributes to the good tribological properties of this system. By means of AFM, we were able to, let's say, to study in more details the fundamental process that drives the phenomena on MoS2, and we are able to find that in the case of amorphous layer, the coefficient of friction is 40 times higher with respect to the amorphous crystalline case. This suggests that effectively the role of water physisorption is the most important one in the case of room temperature. And this results has been also supported by molecular dynamics simulation, even if the, let's say the absolute value are not completely fit what we found in the case of the experimental results. Finally, I would like to thank some people. First of all, Dr. Elisabetta Serpini, who is the main author of this work related to MoS2, and the group of Professor Polsar in the University of Prague for the productive collaboration for MD simulation and for many other issues related to these aspects. And who wants to deepen the aspects related to these issues, you can look at this publication here from our group and from the group of Prague, where you can see in more details what I have already shown. And of course, I thank you for the attention.
Yeah, thank you very much for the presentation. I think it was a presentation that was very complete, starting with the very basics of the theories related to MoS2, going over a lot of experimental insights, and then even closing with molecular dynamic simulations. So I think it was not even just a talk, it was even a lesson to learn something about MoS2, I believe. At least for me, I learned a couple of new things since I'm not working with MoS2.
Okay.
So thank you very much for that. I think we have directly one question from the audience that maybe we can address right away. So there's a question: what is the example of amorphous and crystalline phase coupling? Can we call a 2D material as amorphous and a ferrite phase as a crystalline one?
Yeah, I'm right. I'm reading it. Yeah, of course, it's not really. What is the example? Yeah, I did not get really the question. Can you be more clear? I don't get the question.
I have the feeling that the person wants to ask that if you couple amorphous and crystalline phases, if you can consider a 2D material as an amorphous phase and a ferritic material or ferritic phase or nanoparticles as a crystalline one. But I'm honestly not sure if you can consider a 2D material as an amorphous material.
Yeah, I don't think so. Yeah, I don't think so. I'm not sure that I can answer to this question. But yeah, the ferrite phase, it's not really I would say it's an amorphous materials, but I don't think that we can call it a 2D material. So I don't know if this is the question, but
I think maybe for the moment we can let it like that, and maybe we can also deepen the discussion and also maybe deepen this question after the second talk, and then I would suggest to move on to the second talk, which could be kindly introduced by Philip as well.
Okay.
Yeah, thanks Alberto for the very comprehensive talk. We will come to Professor Carsten Gachot, who is a good colleague and friend, and not to forget, also my boss. Yeah, Professor Gachot is a professor of tribology at the Vienna University of Technology, and he has a profound expertise and background in tribology and material science also. Did a lot of work on surface texturing and also 2D materials, and of the latter he will give us a presentation today with the topic, a new take on the design of in-situ formed high-performing low-friction tribofilms. Yeah, the word is yours, Carsten.
Okay, yeah, thank you very much, Philip, and thanks a lot, Andreas, for first inviting me and for the introduction, and also thanks to Alberto for the very nice presentation. And in fact, yeah, it is a very comprehensive and from the beginning lesson that I also learned at a later time today. So I will try to first, of course, share my screen. That is the first task. Okay, I hope you can see that in a second.
Yeah, it's working.
Yeah, going to the presentation mode, if it allows me. I think I have to switch that somehow, right?
Yeah, we are still seeing the presenter mode.
I will change that quickly, no worries.
Yeah.
Now it's better, right?
Yeah, yeah, perfect.
Perfect. So thanks a lot, as I said, for the invitation. And I would like to talk about the study I did some longer time ago. Actually, this topic, which is presented today, is a work that we did together with Professor Paul Meyerhofer from TU Wien. He's very much in the details of coating deposition and wear-resistant coatings. And additionally, we had Ali Erdemir on board, who is well known to the tribology community. Formerly, he has been at Argonne National Lab, and now he's professor at Texas A&M. So yes, as Philip said, it's about low friction tribofilms, and somehow I found out during Alberto's talk that it really matches nicely with the things I will present in the next maybe 20 minutes. I might be a little bit shorter than Alberto, but then it has also the benefit of having some more time for questions. When we are looking at different ways how we can deal with the improvement of, let's say, tribological properties and how we can tackle actually challenges in reducing friction and wear. I mean, there are different ways how we can do that. And one of the basic things, of course, if you look at the classical machine elements and automotive components that are used still in cars with a combustion engine, and although I would say there is a quite fast victory train of electromobility getting more and more speed in our society, I still believe that there are a lot of automotive and mobility issues in the future that still deal with combustion engines. But apart from combustion engines and components you can see here, like piston rings and and different shafts and parts that are typically coated by wear-resistant coatings or DLC coatings, but also, I mean, if you look at ways how you can reduce the friction in an internal combustion engine, like the things you can see in the lower right-hand picture here, by just using a high-performing lubricant, a motor oil. We also see, of course, developments in that perspective that we are using more and more ultra-low viscosity oils like 0W8 or 0W4, where we have less viscosity and less internal friction in the oil itself, and so reducing, of course, churning losses and other losses, frictional losses in the system. There are a lot of things that you can do, as I said before, and just to give you a kind of a flavor, nowadays there are many things you can put on top of these components, from titanium nitride, titanium aluminum nitride. You can use very much deviating coating systems. DLC was already mentioned. That is not completely new, but still a very powerful way to protect surfaces against friction and wear. Transition metal nitrides and carbides, but also in the recent times popping up more and more in situ forming films based on either MoS2 that Alberto presented before, or also tungsten disulfide. I'm going to talk about today a little bit more in detail, as it has a better thermal stability and load carrying ability compared to MoS2. Graphene, but also things that Andreas and Philip are heavily working on in the society, in the community. MXenes. There was a very nice presentation, by the way, the first presentation given in the 2D mat format by Yuri Gogotsi, who talked about the potential of MXenes. So you can see there's a lot of things you can do apart from using oils, greases, coatings, 2D materials. Of course, you can also use surface texturing, as Philip mentioned before. I've been working in this field for the last 18 to 20 years. Still very fascinating how you can tailor surface topographies to mitigate friction and wear. Well, one point is, and we know this already for decades, and has been used very efficiently for decades in motor oils especially, are additives like ZADP. ZADP is one maybe of the most famous examples that you can find. Zinc dialkyl diethiophosphate that has been used for a long time, very efficiently. But by legislation, step by step over the years, they started by legal issues just to reduce the concentration of sulfur and phosphorus. Now people are looking more and more for substitutions in that area, and they try to maybe in the future to ban that completely because there are some, let's say, increasing concerns regarding environmental issues, exhaust filters in cars, catalysts, and so on, due to sulfur and phosphorus contents. So we have to find a kind of alternatives. So one of the things that has been presented before in different research groups all over the world, I mean, there are a lot of people working in that field, a very fascinating field, that the most promising candidates or the most famous candidates, as I said before, MoS2, graphite as the traditional material, and of course tungsten disulfide, as I mentioned before, that has some advantages, but also some drawbacks that I will discuss in a minute. If you think about how you can actually form these kind of protective layers, I mean, there are different ways how you can apply that. There are sputtering techniques, there's PVD, CVD, there are different ways how you can actually apply MoS2 or WS2 to surfaces. One interesting aspect is if you are able to form them in situ or under the operation given by the load and the temperature and the tribological system involved. And if you want to do that, of course, you need first of all to have a molybdenum or a tungsten delivery system. That is the first thing you need to have. So either you, as I said, you use them as a bulk metal. It's maybe not so attractive and not so interesting for applications, or you make a thin coating on top of the respective surface that you have your delivery system. And then on the other hand, as we are talking about MoS2 and WS2, you need a sulfur delivery system. Where does the sulfur come from? The sulfur mainly can come from, of course, the lubricants that we still need first to carry the load and to transfer the momentum, but also, of course, to carry heat away. And of course, the oils and the lubricants in general have many other functionalities that I will not discuss in detail now. But basically, if you look at a lubricant, then you have different additives inside that have sources of sulfur or phosphorus or something else already implemented. So the idea was that we provide, on the one hand side, as I said, a molybdenum and tungsten delivery system, that on the other hand, by using EP additives, for example, in the lubricant as a sulfur source, that we can create in situ a protective layer of MoS2 and WS2 in the contact. And well, there are also, apart from the EP additives that you can find, of course, commercially available, you may have heard that in this field of getting green, everybody wants to get green now, and we are tackling a lot of these environmental concerns. There are also, let's say, by nature or more environmental friendly sources of sulfur, like diallyl disulfide or cysteine or methionine. So you can find also in nature some of these sulfur sources that are more, let's say, environmental friendly. And that can be used. I will not discuss them today. There is also a very nice publication by my colleague, Dr. Manel Rodriguez-Ripoll, who has done quite a lot of work in that field, and he also published how these additives can be used. Today, we will concentrate on a very, let's say, commercially available sulfur source. It's a commercial Lubrizol EP additive that has been added to a polyalpha olefin 8 synthetic oil, and I will show you what we did. So first, the idea was, this is a kind of an overview sketch of the in-situ generation of these tribofilms. I will come back to this during my talk, step by step. So the basic setup that we selected is a ball on disc setup under unidirectional sliding. You can see that we have a sliding speed of 0.1 meters per second. As I said before, we have a polyalpha olefin lubricant that is used here for as a synthetic lubricant with an EP additive as a sulfur source, and the additive concentration has been varied within this from 0% to 5%, and all the tests have been done at elevated temperatures up to 100 degrees C. When we start with a very simple reference test, we say, okay, the reference is a bulky molybdenum sample, and we take as the counterbody a silicon nitride ceramic ball. We selected silicon nitride because we say it's much harder, it's inert, not reactive to the molybdenum sample. And we start doing our test. You can see coefficient of friction versus time. And then you step by step, you are adding. On the one hand side, you're looking at the situation where you have no EP additive at all. And on the other hand, you are looking at the situation where you can find actually 5% of an EP additive. And it's rather remarkable to see what happens if you add 5% of an EP additive. So the friction coefficient drops down significantly by just adding 5% of the sulfur source. So on the one hand side, we have very high wear. On the other hand, we have nearly no measurable wear. You can even see that for the situation, no EP additive, there's a lot of oscillations and fluctuations here in the frictional signal. Whereas for the blue curve here, for the 5% of the EP additive, apart from the fact that we do not really measure wear, the curve is rather smooth and there is not so much oscillation. So basically, the formation of MoS2 under these conditions is working. And now the next question was, okay, if it is working for molybdenum, how does it behave actually with tungsten? Tungsten, especially tungsten disulfide, as I mentioned before in the introductory part, has some benefits. It's in terms of temperature more stable. It has a higher temperature stability, but also the load carrying capacity is enhanced. And so we gave it a try. If you're looking at what actually happens, if you maybe just a few comments more on the tribofilm itself and the debris around the wear scar. You can see there is a lot of debris around here. We also did XPS here, so you can detect the sulfur from the sulfides to some extent. And when you look a little bit more closely to this red encircled part, when you do Raman analysis, we took as a comparison here the Raman spectra for the silicon nitride, also for the PaO8 with the additives. You see here the characteristic spectrum of MoS2 with the characteristic wave numbers here. And you see what happens in case of no EP additive and 5% EP additive. So clearly, also by Raman spectroscopy, you have a very pronounced evidence that you actually form MoS2, because the signals here and the peaks are very much the same that you can find here. Then I said before, okay, what happens if we do the same with tungsten? So can the reaction occur despite tungsten has then stronger bonds? It's from the chemical side not as reactive. It's similar to molybdenum to some extent, but you can see when you start adding now step by step the EP additive, so 0.5, 1.5, 3%, and even 5%, there is a drop down in the friction coefficient compared to the situation no EP additive on board, but it was not so small as we expected. And the question was, why? What is happening there? When we go a little bit further, and we study the wear tracks, we can see that we have high abrasive wear. There's micro-plowing marks that you can identify. When you do the XPS, actually the amount of the tungsten oxides is first rather small. So compared to the molybdenum side, where we had a large amount in XPS also of metal oxides that could be identified, for the tungsten system, there's a small amount only of tungsten oxides present, and there is no evidence of sulfides in the contact. So obviously something does not work properly. The question is now why? When you look at the Raman spectra, this again shows you very clearly that for the 5% of the EP additive, you don't see any peaks characteristic for the WS2 in that case. So the idea was to say, in the molybdenum system, we found a lot of oxygen and oxides. And in the tungsten system, there was not so much oxide present. And also Alberto mentioned already in his previous talk. So the oxygen can have different roles in this scenario. So we try to say, okay, maybe something is going on with the role or the influence of the oxygen. So the next experiment, actually what we did was to take a tungsten flat sample, and we annealed that at 600 degrees C under ambient conditions. And then we created, after 15 minutes, this thermal treatment, a very homogeneous and 500 nanometer thick tungsten trioxide film. So we pre-oxidized the tungsten surface, and then we checked what is happening after we pre-oxidized it. And again, we start 0%, there is no EP additive present, coefficient of friction versus time. Now we start to add slowly, step by step, the additive. And what you see is first, nothing happens, but then for higher concentrations, once you reach a certain threshold, there is a significant jump of the friction coefficient down to very low values, up to 0.05 in the friction coefficient, which is rather small. So obviously, when you reach a certain threshold value of the additive concentration, then you have a very pronounced and emphasized drop down in the coefficient of friction. And obviously, this approach by pre-oxidizing the tungsten surface had an effect on that. Now we have to understand why. So there is actually two parts, initial reaction and breakthrough reaction. If we look a little bit deeper to that. So again, you see the wear tracks or the micrographs for no EP additive and 3% EP additive. And if you then do XPS and EDX on the oxidized surfaces, you can learn quite a lot. Also, if you just simply look at the ball surface, the counterbody, you can see if you don't add an EP additive, you see a severe flattening of the ball. And if you add already 3% of the EP additive, the ball surface is not flattened, there's much less wear, and we have the significant jump down in the friction coefficient. When we look a little bit more deeper in details, again, the comparison of the Raman spectra for the silicon nitride, so the ceramic counterbody, the PaO8 with the additives on board, the WS2 spectra. Also for the tungsten trioxide, we can clearly see that if you increase the concentration in EP additive from 3% to 5%, that you step by step start building up the characteristic peaks of the tungsten disulfide. You can also, for the 3% EP additive, clearly see the peak of the oxide, of the tungsten trioxide. And when we look a little bit more on there, we said, okay, now we understand that when we do this with a pre-oxidized substrate material tungsten, what would also happen if we start revisiting again the MoS2 formation? So we just exclude the oxygen from the test, and we do that in dry nitrogen atmosphere. So just as to remind you, we had the scenario before, no EP additive, and then we added the 5% EP additive under ambient air. So once you start, of course, doing the test in dry nitrogen atmosphere, you see the coefficient of friction goes down, but it is not as low as in the scenario before under ambient air. So there is a significantly higher coefficient of friction, and obviously, as I said before, the oxygen plays here a very important role. So coming to a kind of an intermediate summary, it seems like we need a balancing of the system. So, you know, there is a kind of equilibrium that is governed by two things. First, of course, we need a sulfur source. We have a limitation by the sulfur availability that comes from the additives in the lubricant. On the other hand, we have a limitation by the oxide formation and consumption, because when you do the sliding test, of course, you are mechanically removing the tribofilm that is forming, and you also create it again in the contact and you replenish the contact again. So you need to find a very defined balance between sulfur as a delivery source, oxidation rate of the material as an intermediate approach, to find the optimum parameter that you can in situ form the molybdenum disulfide and the tungsten disulfide, and then to tackle the friction and the wear. So we also try to understand, okay, how does that go hand in hand? Because we know that the tungsten trioxide actually is rather stable. When you start increasing the temperature, with increasing temperature, of course, the stability goes down. You have a decomposition of the tungsten trioxide. We also did some DFT calculations where we try to investigate the effect of contact pressure on the stability of the involved phases or involved compounds. So when you look at this formation enthalpy versus the contact pressure in gigapascal, you can clearly see the higher you go with the contact pressure, the more stable actually the tungsten disulfide gets. So we have a kinetically hindrance in the beginning, but by the interplay of temperature and contact pressure, you might even push the system to a higher stability of the tungsten disulfide in the system, which is not to be expected because usually the metal oxides are rather stable and you can find them predominantly in the contact. But by raising the temperature, by raising also the contact pressure, you can even shift the system. And this is clearly proved by the DFT calculations, where you have a region with a more stable tungsten disulfide that is sketched here in red. You see that this blue line here indicating the tungsten trioxide, there's a crossing point here or a junction point where the WS2 actually starts to be more stable. So we said, okay, fine, but who is using, by the way, pure tungsten surfaces? No one. Also, there is a problem with the tungsten delivery. So we saw that in case of MoS2 or molybdenum surfaces are more voluntarily forming MoS2 in situ. In the case of tungsten, there are some complications. And also in terms of, as I said, the delivery system of the tungsten, there are some drawbacks. So we decided to go actually for tungsten nitride coatings. Why? There are two reasons. The first reason is, first, tungsten nitride has a much higher oxidation rate, surface oxidation rate, that actually helps regarding what I explained before, to have this intermediate pre-oxidized state, that it actually can happen that you form tungsten disulfide. And the next point, the second point, is that, of course, the tungsten nitride is much harder than the pure tungsten surface. So we produced tungsten nitride coatings by high PIMs here. We had a hardness in our experiments of 31 gigapascal. As I said, it was reactively sputtered. And we also cross-checked then that we actually ended up with the right composition. When you do that, when you really look at tungsten nitride coatings, as I said, higher hardness, better tungsten delivery system because of also a better surface oxidation rate compared to the pure tungsten, what can you expect? And then we started actually again to look at the coefficient of friction over time, also for different contact pressures. Again, we were using a system, silicon nitride versus the tungsten nitride coatings, this case only for 5% of an EP additive, where we knew before that it actually gives us the best results. And what we can see is actually that all of them, they start at a very low coefficient of friction, but the higher it goes with the contact pressure or the higher the loads are, we see that the coefficient of friction is increasing. So higher loads wear the tribofilm away. We have a mechanical removal of the tribofilm and the coefficient of friction is higher. But if you look at more detail, what is happening actually to the surfaces, this is a sketch from the ball surface, from the counter surface. And again, you can find on the right-hand side the Raman spectra for the different scenarios, for the different contact pressures. So you can detect also for the 0.9 gigapascal, the characteristic peaks of the tungsten disulfide in the system. We also can see that around the rim on this ball surface here, there's a lot of debris coming from the tribofilm that is moved away, that is replenished again, reformed again. But actually also, even if you have a higher friction coefficient and you have a high contact pressure, still, of course, you're forming the tungsten disulfide. And when you look a little bit more detail into the wear tracks, we did some SIMS, secondary ion mass spectroscopy, where you can even see that especially the side tracks of the wear parts, of the wear patches, they are very much enriched in sulfur and they are depleted in oxygen. So oxygen is consumed by the system. Sulfur enrichment takes place, which again validates and proves also the scenario of the tribofilm formation. This is one part that needs to be considered, of course, but if you go a little bit more ahead, you can also see clearly on the counter faces, no additive, severe flattening of the ball surface. If you add the additive, it really reduces, even for higher contact pressures, the wear on the counter body. But as I said, this is one part of the truth. The other part is actually directly connected to the structure of these, let's say, fragments that are formed in the tribofilm. So we did some TEM investigations, and you can see that most of the things that we observe are actually amorphous. But we can also identify, I hope you can see my mouse cursor, we can see there are some patches, partially crystalline patches forming in this tribofilm. And you can also maybe slightly see these kind of line-like patterns here within these circles. And when you measure that, you actually come up that when you measure the distance here, the plane distance, the lattice spacing, that this corresponds very nicely. In this case, I'm sorry, this is a typo, should not be MoS2, should be WS2, that we form actually the tungsten disulfide very locally in the tribofilm that is still mainly amorphous, but you have this growing islands of crystalline patches in the tribofilm. And one other prerequisite actually for a working tribofilm is that you have a very nice alignment alongside these lattice planes. And on the other hand, of course, as I said, the tungsten delivery and the oxidation process taking place before. So this is a very final proof that in this film, we actually found islands of tungsten disulfide that can be easily proven by the lattice spacing that we measured in TEM. And to make a kind of a summary now. So when you are looking at the in situ formation of tribofilms in these two systems, it highly depends on, as I said, first, you need to have very much a formation route via oxides, especially for the tungsten. This is decisive. As I could show you, if you don't have a pre-oxidized surface or something that has a high surface oxidation rate, you will not be able to form in situ the tungsten disulfide. You also need, of course, a respective additive source that provides you with the sulfur. You also have to provide, of course, the tungsten or molybdenum by itself. And the final point that I could show you by the TEM investigation is that you need a kind of a self-orientation of these partially crystalline forming fragments in the tribofilm that are then subjective to shearing, that you have all this coming together to make it work. So I hope, at least, yeah, time-wise, it's okay. I hope that I could show you that there is a lot of things to be discovered still in these interesting systems. And of course, I would like to thank you for your attention, and I'm happy if you have any remarks or questions later on. Thank you very much for your attention.
Thank you very much, Carsten, for a presentation of a very innovative project, I would say. Yeah, we had a question before, but and I wanted to invite the person, since apparently it wasn't quite clear to Alberto what the person was asking, to ask himself, but I think the person has already left. So yeah, we would like to invite everybody to ask some questions to both speakers now, if you have any doubts or remarks. Ready for you now.
People are already exhausted by the time.
Yeah, there's a question coming in now. I don't know exactly to whom it is. I guess yeah, to Carsten, because he was showing TEM. Could you please elaborate how TEM of interface film was carried out?
Yeah, this is a tedious task. Actually, I mean, this is a work that was done by our PhD student, Bernhard Kohlhauser, who did his PhD work in this topic or on this topic. And of course, it was not easy. It's like finding the needle in the hay heap, I would say. Yeah. And everybody who did already a TEM preparation knows how difficult it is actually to prepare such a film. That it survives, and even if it survives, that you can find what you wanted to see. So it took him hours and days maybe to do the TEM investigations. I mean, I cannot tell you all the details. The standard procedure, of course, is you do some FIP cross-sectioning, and then you are putting some protective platinum layer on top. And then you have a very much, I would say, standardized routine in the focused ion beam microscope, how you prepare it for a TEM cross-section. So you have these marking crosses, and then you are cutting out actually the slide. This is all done in the FIP machine. And then you are actually welding it to a manipulator like a needle. And once it is sticking to this needle, then you just look that it is, so to say, free to be taken out, and then you are gluing it. I say it in a very simplistic way. Of course, it's much easier, much more difficult, I wanted to say, as I describe it. You're gluing this then to a TEM grid. There's a copper grid, and then you go to your TEM, and then you do your TEM. So there are many steps. I now made it in a kind of a very simple way, but actually everybody who did that before knows that it is a very tedious task. You have to be very patient. Also a bit of luck, I would say, is needed to find what you wanted to see. I hope this was now quick, but I hope it somehow answers your question. Yeah.
I think the person's happy. Yeah.
Okay, then I'm also happy. Yeah.
Yeah. To break the ice a little bit, I have a question for Alberto. I mean, we know MoS2 since a long time, for decades now, and we are still exploring MoS2. But what do you think? What is going to be the future of MoS2? Where do you think should research point towards? What are the research gaps we don't understand? Where should people look at if they're really interested in to do something in this area?
Yeah. Well, in my opinion, we have space, I think, in the characterization, further in the understanding of the fundamental processes, because up now, okay, we started to get deeper in these details, but we did not get everything about the material. And there is space in particular in the characterization, in the, let's say, in the study of isolated layer of MoS2. So for example, what we dependently made with graphene can be done also with MoS2, and I don't think that there are so much study in this let's say in this field, and this is for fundamental research. Related to the application, I think that the most promising way in order to use MoS2 is using doping in order, for example, to improve its properties also in humid ambient, because I showed that it is possible if you slightly hit let's say the system to avoid the failure of this material, but probably using a doping that can trap in a way the water molecules or something like that, you can get most promising results in terms of performances. And the other, let's say, the other solution that we tried years ago, but let's say with not really good success, is to use MoS2 as additive, for example, generating, let's say, we know that MoS2 has not really good mechanical properties because it's quite soft and so on. So it's very easy to wear it out. And so one way is, for example, to generate a matrix of an hard materials with the addition of MoS2. But in this case, there is the problem of how MoS2 grow inside another matrix. So if it is, let's say, if it forms microcrystallites, or if it forms some bonds with this matrix and so on. So I think that there is space in this, in the case of really application of MoS2 in order to improve its performance.
Right.
This is my idea.
Mm-hmm. I have another question which can go to either speaker. Maybe we can start with Carsten, and then maybe Alberto can also share his opinion. I mean, Carsten, there's a lot of people. I mean, working on 2D materials is a nice thing, but there are a lot of people that even work on hybrid systems. So means the combination of two 2D materials, for example. So if you consider, for example, the systems that you have been working with and the results that you have been showing, could you imagine that you could imagine any kind of synergistic effect combining both materials that you showed, or which materials one would need to combine to see these kind of things?
No, Andreas, this is a very complex question. Of course, of course, it is possible to combine them. In the case of MoS2 and WS2, I think it doesn't make much sense because each of them, they have their benefits or advantages and disadvantages. I mean, MoS2, Alberto knows that better than me. He's working in that field much longer. MoS2 is very prominent, very famous for space applications, and still is one of the materials or one of the compounds of choice, first choice for space applications. If you look at projects regarding satellites or everything that is related to extraterrestrial, this is really MoS2 is the way to go. WS2 has of course, as I mentioned in my presentation, some potential, some advantages. The combination of both in that case, I would say, doesn't make sense, but there are of course ways how you combine. I mean, we know also from other colleagues, from Andre Vovodin, also by these chameleon coatings, where you really stagger up different materials, where every material in this layered system is taking a functionality. So they can be graphene combined with MoS2, can be combined with DLC. So there are many things where you try to cover as much as possible in a multi-layer stack. But of course, you have to know how you combine them, and also you have to know how they interact with each other. So it must not be always synergetic. It can be also detrimental in a way that they are hindering each other or blocking each other. And then the processing approach is another challenging task. It's not just putting all over another and then to see what's happening. You have then intermixing and mechanical mixing, and maybe you destroy the functionalities of each layer. That is a very quick answer. I would say in my particular system, I would say it doesn't make sense, but I can imagine some occasions where it is definitely of interest. Yeah.
Alberto, do you want to complement something?
Yeah, no, I have not really much more to add. I mean, I completely agree with Carsten. I mean, it's a very complicated, very complex question. I would let's say I would repeat again what I told. I mean, we know the properties of MoS2, and if I can imagine to implement the material, I would let's say I would look at another completely different material in order to, let's say, to fill the void that MoS2 has, for example, the mechanical properties. But I do not have any idea about the combination of two different solid lubricants. I mean,
right.
Maybe it has no sense. I don't know. I don't know. Probably I would focus on other aspects, so that the thermal stability or something like that, for example.
Right. Excellent. There's another question from the audience. Goes to Alberto. Can you comment on the use of MO oxides to in situ form MoS2 as tribo layers?
Okay. Really, I don't know really what can be the let's say the real aspects related to MoS oxides. I mean, what we know is that its presence is usually detrimental for the sliding process, and of course this depends also on many other parameters such as the temperature, because this is important also in considering the sliding process. What is my experience is that it's not really let's say it's not really so critical, the formation of the oxides. I mean, it depends on the temperature. If you look at the literature, they say that if your system is working at high temperature, you have that oxides is the dominant process in terms of MoS2 failure. So this depends mainly on the working condition and also on the methods that you use in order to grow the MoS2. I don't know if I have answered the question.
Maybe just an additional comment from my side.
Yeah.
It's very funny to see the role of the oxygen in general, because Alberto, what you presented is if you already have the MoS2 and then you're using it under ambient conditions, or you have the oxygen on board, they might be very detrimental. Yeah. But in the first step, if you just have, imagine you just have pure molybdenum or pure tungsten, then of course, if you are not doing it under oxygen environment, the in situ formation is blocked. So you need somehow the pathway via the oxide route to get to MoS2 or WS2. But once you have it, and then you are still doing it under oxygen atmosphere, it's not good. Yeah. So to a certain extent, oxygen is good, and then later on, it's not good anymore. Yeah.
Yeah.
That's very interesting to see what is the role of the oxide, or the role of the oxygen in general. Yeah.
Yeah, maybe also a question from my side to both of you. You were talking about transition metal dichalcogenides now, and Carsten was also showing, of course, that you can exchange the transition metal. And one of our last speakers, actually Martini, she showed that you can, of course, also exchange the chalcogen. So she showed, for example, very promising results for tellurium. Do you know anything about that? And do you think that could maybe be another material which is worth investigating, also not only with MD or on the nanoscale, but also on the macro scale?
Yeah, okay, I can, yeah.
Alberto first, maybe.
Yeah, I've never investigated other kind of composite like this. My opinion that it depends also on, let's say, we have to look also at the at other aspects, such as the cost, which is related to the usage of this material. I think that the use of MoS2 and WS2 is also related to the cost in the production of these materials, and also it is related to, for example, in the case of tellurium. Tellurium is a dangerous materials if it decomposes in its pure, let's say, in pure amount, and this has been taken into account also, let's say, at this age where also the disposal of material is important. So yeah, of course, for basic research, it has sense to study new solutions, new material, and so on. But I think that we have also to take into account the boundary conditions. So, for example, like the cost, because every time that we are dealing with new materials, we have also to take into account the cost, and also other secondary effects, such as the health and so on. Related to, let's say, to the scientific aspects of this new, eventually new material, I have no idea. I mean, I don't know how they can behave. I know that there are some words related to this kind of material, but I can't do any provision about that.
Yeah, I mean, if you are in the periodic elements table and you are looking at this line from sulfur down to tellurium, of course, what we know is if you go from sulfur to selenium to tellurium, that it is actually the more down you go to tellurium, the more chemically stable the layers can be, and it's also expected from some ab initio calculations that you might end up with a lower or easier shear compared to if you stay with the system MoS2, and then you would say, okay, I go for molybdenum diselenide or molybdenum ditelluride, then you should have a better friction behavior. But I totally agree with Alberto, because you can imagine a lot of funny 2D materials or TMDs, a lot. And one thing that we really neglect is, because we are right now working with Philip in a very similar topic, and Philip knows what we ordered. There are some of these substances are rather poisonous. They are very toxic. So you do not want to inhale them or to touch them with your skin. And even as a disposal, as a waste product, you do not want to let them out in the environment. So one aspect is you can have something really fantastic, magnificently working in friction and wear reduction, and you say, wow, that's the material of choice. But once you create a lot of waste and the things are very toxic and the costs are high, as Alberto said, that is completely useless. So you have to find this balance between, it must make sense, of course, in terms of properties and application. It must be relatively easy to be produced and not too expensive, and waste disposal. So environmental concerns are very critical nowadays. So whatever you develop, whatever you discover, and I mean, this box of periodic elements is so huge that you can imagine of millions of combinations of elements in this table. But what comes out, is that toxic? Is that expensive? Is it easy to be produced? So these are things we as scientists also have to take into consideration. Yeah.
Sure.
Okay, I believe that there are no further questions from the audience. So I think the last thing what we have to do is to thank our speakers for both inspiring talks. I think it was very interesting, very nice to see both of you, at least online, and to learn something more about 2D. Hopefully the next meeting is going to be in 3 dimensions, as we always joke, but no one knows when this is going to happen. So the last thing, of course, we wish to thank our sponsors, which is the MDPI journals, Coatings and Lubricants, as well as Frontiers of Mechanical Engineering, and from the industrial side, Artec is also sponsoring. So we are very grateful for that. And now we can announce that in the next Christmas session, we're just going to have 1 speaker, but the Christmas present for all the 2D Math people is going to be Rob Karpik, who's going to be for sure giving an inspiring talk about AFM tribology and 2D materials. So from this sense, I thank you very much for your attention, and maybe Phil wants to close this session now.
Yeah, thanks again, Alberto and Carsten. Were really some very interesting talks, and I guess everybody who took place learned a lot. And of course, thanks also to the audience for taking place. And yeah, stay safe and see you next time.
Philip, there's one question. I mean, one colleague is having a question. If we are okay still with the time, maybe we can allow this short question to the colleague.
Yeah, sure. I didn't see that. Thanks for making me aware. Yeah, go Sandan.
Yeah, Dr. Sandan here. So I have been working on TIC and Cermet, and that we have prepared using molybdenum sulfide. And the interesting point is when we did the tribology testing against tungsten carbide ball, so at around temperature 500, we found like, okay, there was a worm-like structure. It is like, okay, it seems like worm. So because of that, like when we increase the temperature up to 300, we got more wear with the tool, with the TIC and Cermet. But when we reached to 500, at that condition, we found some worm-like structure, and friction and wear both got reduced. So whether it is because of molybdenum sulfide or tungsten sulfide, that we are not able to conclude, because we did not go for Raman or some analysis, because that time we thought maybe this is molybdenum sulfide, but usually I found in the publication, in the papers, it is tungsten sulfide. So is it come from tungsten carbide ball, and tungsten carbide get reacted with sulfur at around 450 or 500 due to stimulated condition of friction and stress and wear? So that was my doubt. If anybody had any experience about tungsten sulfide at around 500, it get worm-like structure.
I have not seen that before, but yeah, the easiest way, of course, is if you do some analysis to find out what it is finally. I mean, it cannot be excluded what you described, but of course, I'm not familiar with your particular setup. I mean, the easiest thing really is to do some chemical analysis to have a better understanding. But regarding this worm-like structure or morphology that you described, I have not seen that before, so I don't know.
So yes, what I'm thinking is I will share this with Professor through the email or at LinkedIn, because I have that picture. ACM I have done, and ACM I did up to 2 lakh magnification. But unfortunately, I lost the sample, and I could not go for other chemical analysis. So I'll be sharing that picture with the professor, and then we'll have some conclusion over this.
Yeah, perfect. Sounds good.
Yes. Okay, thank you. Thank you so much.
Okay, then I guess that's it. Take care again, and see you soon, 3D.
Thank you.
Thank you.
Thank you very much.
Bye-bye.
Thank you very much. Take care. Stay safe. Bye-bye.
Bye, everyone.
We also invite you to submit your research to 3 current special issues in Coatings, Lubricants, or Frontiers in Mechanical Engineering. You can find the links to the special issues in the comment section below the video.
Introducing the most advanced universal tribometer, the MFT 5000. With a modular architecture platform design, it is a robust surface testing instrument engineered to evaluate friction, wear, mechanical properties of materials, as well as lubricants over time. The MFT5000's open XYZ stages and wide range of interchangeable modules and sensors allows users to self-implement and add-on customization and combine several tribology tools all on one device. These diverse modules accomplish various motions for any application and are capable of speeds from 10,000 RPM to 500 Hz oscillation. The complement sensors achieve millinewton to 12,000 Newton wide force range, with options of strain gauge, piezo, and capacitive multi-dimension force sensors. The lambda profilometer, combined with the patented inline design, coincide to analyze any surface, including glass, with ease. Because of its unique four imaging modes, the profilometer produces 3D information by creating sub-nanometer surface images automatically. A fully automated and simple software interface integrates the data, enabling researchers to design and conduct tests at nano, micro, and macro levels. To simulate real-life scenarios, the tribometer comes with several environmental control options that allows testing -120 to 1200 degrees Celsius temperatures. These interchangeable chambers are skilled in evaluating high pressure, vacuum, humidity, salt spray, and tribocorrosion conditions. Due to its multiple possible configurations, the MFT5000 is used extensively across a wide range of industries, including oil, biomedical, semiconductor, coatings, automotive, electronics, materials, aerospace, and many more. On this platform, all types of tribology tests are possible. Our tech instruments, leading innovation in tribology and surface test instrumentation.